All right, so like I was saying, the extent of my skill in art is drawing boxes and stick figures. So you're going to see a lot of those this semester. Uh, let's say we have two people playing catch. The most important now, despite my lack of artistic skill, the most important thing I'm going to teach you this semester is how to draw a picture. I know it doesn't make a whole lot of sense, but that is going to be step one of our problem solving process for the entire semester. We're going to draw a picture. And the reason for that is there's just too much detail for us to keep it all in our minds, and putting it down on paper lets us actually be clear about what we think is happening. Step two for problem solving is going to be to specify what our coordinate system is like. So in this case, we have two people throwing a ball back and forth. We want to decide which direction is the positive x direction, which direction is the positive y direction, and we want to decide where the origin is at. So in chat, any good ideas for where we should view this game of catch from?
I would say the red character.
Yeah, that is a very reasonable answer. So if either the red or the blue, they would have been equally reasonable. So at what height do we put our viewpoint, though? Are we going to say, well, the origin is down here? Or do we say it's at eye level of the red character? Or do we say that it's at throwing height? Right? In the end, it generally doesn't matter where you decide to put the origin. It does matter that you pick some place and that you stick with it. So once you have made your decision about where your perspective starts from, you have to stick there for all of your analysis for the rest of the problem. So I think it's really reasonable to make the red person our point of view, and I'm going to choose the throwing height as the origin. Also, I'm going to go ahead and say that to the right and up seem like reasonable choices for positive x, positive y. Okay. Then we get to step 3. And this is the step that we're going to spend a while talking about this morning. Vectors. Because I am willing to bet that the only experience any of you have had with vectors is one day in Algebra 2 where you briefly covered it and then never spoke of it again. Does that sound more or less right? Yeah. All right. There are some things that we want to say about vectors. So your book will say something like a vector is a quantity that has a direction and a length. And that's true. So say here's a vector. It is true that this thing has both direction and length. However, that's not a super useful way of thinking about vectors. We can't solve problems on that definition. So instead, I like to think of a vector as the hypotenuse of a right triangle. Now, right triangles are something we know an awful lot about. In fact, in high school, chances are you spent an entire semester on right triangles. So if we can leverage what we know about right triangles to help us analyze vectors, we're going to be in a good spot. So let's say that we know the direction of a vector, that is the angle it makes with the horizontal, and also the length of that vector. How is it that we would get at how much at the x part of the vector and the y part of the vector? See a couple people saying trig. Yep. That is definitely correct. Cosine and sine, SOHCAHTOA, yeah, you guys are on the money. So if we want to know something about the a sub x here, well, we could definitely use cosine to help us out. So the cosine of our angle is going to be the adjacent leg over the hypotenuse of the triangle. In this case, our adjacent leg is going to be the x part, and the hypotenuse is going to be the length. So if we just wanted the x part, we could say that the x part of the triangle is going to equal the length times the cosine of the angle. Boom. Similarly, we could write down that the sine of the angle is the y part of the triangle over the hypotenuse, or that the y part is equal to the length times the sine of the angle. All right. So far, so good. What if we were going the other way, though? What if we had the legs, right, the AX and the AY, and we wanted the angle and the length? Right? Maybe let me change color a little bit for this. You all will notice that I'm a big fan of using lots of colors. All right, so how can we get the orange quantities in terms of the purple quantities? Well, the hypotenuse is the easy part. We've got a very famous theorem that tells us how to do that. Right, this should be everybody's second favorite formula, right? And we have one more regular trig ratio that we haven't used yet, and that's the tangent. So if we need to get that angle, we can use the arctangent. All right, and let's talk a little bit of notation here. When we are keeping track of the x and y parts of a vector, I like to use these angle brackets. So we use an arrow on top of our variable name to indicate that it's a vector and not just some number. And then we have an angle bracket, x part, comma, y part, close angle bracket. This is a notation that mathematicians use more often than physicists, but I like it. It keeps our vectors from looking like they're points, and it also keeps all our information nice and compact. So technically, we use these absolute value signs around the vector to mean the length. And when we say that this is the magnitude of the vector. But sometimes when there's no risk of confusion, instead of writing vertical line, A arrow, vertical line, I'll just write regular A. And we'll just let that stand for the length of the hypotenuse. Again, it is traditional to use capital letters to name vectors and Greek letters to name angles, but when you're turning in work, do whatever you want as long as it's clear what's what. Okay, so this is how we describe a single vector, but that by itself is not super useful. We'd actually like to manipulate multiple vectors together. So let's say we had a second vector there are some things that we might want to do with these vectors. And the first thing that we might want to do is add them. So if A, say, is the description of the first leg of a hike that you're on, and B is the description of the second leg of a hike you're on, then adding them together will give us the total ground that you've covered over the length of your hike. Adding vectors is relatively simple. We just add their components, and that becomes the components of our new vector. For most of the class, this is all you'll need to know about vectors. There is one other thing that we'll add for one chapter about halfway through, and we'll need a way well, actually, let me back up. There is one other thing that we're going to need to do on a fairly regular basis, and that's multiply a vector by a constant, by a scalar. There was a question about how these look graphically. Don't worry, I'm going to draw that out in a second. This C in black, numbers that aren't vectors, we call scalars. And we call them scalars because if we multiply a vector by them, they don't change the direction of the vector, they only change how long it is. That is, they scale the vector. Later on in the semester, we'll talk about how to multiply vectors together, but that'll end up being pretty simple. So if we have our vectors A and B, say here's A, there's the first leg of your hike, and then the second leg of your hike is like so. So this is B. This is A. then A plus B goes from the beginning of A to the end of B. You're going to do a lab on this, I think, not next week, but the week after. Similarly, if we start off with A and we scale it up, well, there's CA. This is assuming that C is bigger than 1. If C was smaller than 1, we might have a little tiny thing here. So this could be CA for C less than 1. And if C was negative, then that would have the effect of flipping the direction of the vector. All right. Are there any questions about this math stuff before we jump back into physics? Juliana asks, is there anything due from lab today? Nope, I think labs start next week. And yeah, you don't turn that into me, it'll be your lab instructor. Any questions on this math stuff? Because we're going to use this all semester long. C is still scalar if it's negative, Casey asks. Yeah, we still call it a scalar because it doesn't rotate the vector. It just flips it. Yep, we're definitely going to apply them to some problems. Don't worry about it. So going back to our baseball problem, there are some things that are vectors that we might need to consider here. In this first section, we're going to talk about what's called kinematics, which is just how things move. Nothing about why, that'll be next week. But for now, just what kind of movements do objects make? And the movements that they make depend on the position they start with, they depend on the velocity they start with, the acceleration that they undergo, this first object here is a position, right? So I try to use S's for positions because we're already using X and Y's for coordinates, so I don't want to confuse it too much. And then the subscript 0 means at time equals 0. For all of the first chapter, we are only going to consider situations in which the acceleration is due to gravity. So for all of the problems that we're going to consider today, the acceleration is going to have no effect horizontally, and it's going to affect vertically at a rate of g, where here g is approximately 9.81 meters per second squared. I am almost certainly going to round this to 10. I know that makes me a dirty approximator, but I also don't want to have to pull out a calculator every time we do a problem. And then the last thing that it depends on is going to be time. How long do we let this thing move? So let's talk about what each of these things mean. Right? Position is the easy one. It's just where is the thing? Right? So for example, at time equals 0, in this picture, the fellow in red is throwing the ball. So for time equals 0, we've just thrown. So the initial position of this ball is the origin. Now the velocity of the ball right? 'Cause we didn't just throw a burning fastball right at the chest of our friend. We kind of lobbed it up a little bit to give them a chance to catch it. Let's say that we can throw a ball at a speed of 6 meters a second. And let's say we lobbed it at an angle of 30 degrees. Is that VOL? These are the magnitude arms from the last screen. So the length, the magnitude of the initial velocity vector is 6. Jolene, that's a really good question. So what do we mean by velocity? So position's the easy one to define. Velocity, what we mean by velocity is the change in position over time. Right? So velocity is the rate at which an object changes position. So how much of our velocity is going to be in the x direction? How much of our velocity is going to be in the y direction? Would the magnitude be considered as distance then? So that's a really good question, but no. So the magnitude, saying that the magnitude of a vector just means that's how quote unquote long the hypotenuse is. But by saying, so maybe length of the hypotenuse here, like there's a little problem with language, but just because we say that something has a length doesn't mean it's a length through like physical distance, right? Because we can, I mean, we're in English we're used to thinking about lengths of time, right? So we just need to stretch ourselves one more step and say there's also lengths of velocity, lengths of, right? And we actually call that speed. So while the velocity considers both how fast we're moving in the x direction and how fast we're moving in the y direction. if we are only interested in the magnitude, wow, that was a really messy bit of writing. I apologize. Yeah, so velocity is speed with direction. So if you are driving on the 95 to get to work, you might say that you're going 75 miles per hour. That would be your speed. 75 miles an hour north would be your velocity. All right. So let's look at our velocity in more detail here. So fellow in red is throwing this ball 30 degrees above the horizontal with a speed of 6 meters a second. How much of that speed is in the x direction? How much of it is in the y direction? Well, we can use our tools that we developed on the last page and say that, well, the x part here has actually got to be hypotenuse times cosine of the angle. And in the y direction, it's got to be hypotenuse times sine of the angle. So we can go ahead and fill that in. Yep. Thank you, Kyle. Kyle has done the evaluation of the sine and cosine for us. So sine of 30 is a half. Cosine of 30 is square root of 3 over 2. And we actually need to make one more alteration here, since way back at the beginning of this problem, we decided that to the right was the positive x direction. This throw is actually going in the negative direction. So we tack on a negative sign there. Negative sign on the x velocity, the initial x velocity. So all right, we are still on step 3 of our problem solving method. Negative because it's going to the left? That's right. When on step 2 of our problem, we said that to the right was positive, but because this ball is going to the left, that's the negative direction. So its velocity is negative in the x direction. Did that answer your question, Logan? Sweet. All right. Step 4 may surprise you. Now and only now do we do some physics. And this will be typical of the problems that we encounter this semester. Most of the work will go into just stating the problem clearly, drawing a picture, breaking up vectors, making it so that the very few tools that we have at our disposal can actually chip away at what we want to know. So I guess it's time to actually talk about what tools we've got. As of today, if you have read chapters 2 or even 3, chapters 2 and 3 have a combined 3 tools, 3 formulas that are worth memorizing. And they all actually just come from our definitions of position, velocity, and acceleration. So let's talk a little bit more deeply about those. So we might say that we have a position, which has got an x and a y component. Frequently, we are also going to be talking about a quantity called displacement. And what we mean by displacement is the vector difference of where you ended up minus where you started. And if we remember a couple of pages back, if we want to add or subtract vectors, we just add or subtract their components. And then there's the concept of distance that we're going to talk about too. So displacement is a vector because it's the difference of two vectors. Distance is the magnitude of that displacement vector. In other words, we have to use the Pythagorean theorem. Here's an analogy that I like for explaining these 3 things. Let's say it's January 2nd, and you're getting up to fulfill your New Year's resolution of jogging 2 miles every day. So you get up, you jog a mile to the nearest Starbucks, you grab yourself a coffee, you drink it, and then you jog a mile back to your house. So it is very reasonable to ask, first of all, what is your final position? What is your initial position? what is the displacement that you underwent, and what is the distance that you jogged. So you started at home. We're going to call that the origin. However, you also ended at home after jogging to Starbucks and back. So your final position, also the origin. So what is your displacement? That is, what's the difference between where you ended up and where you started? It's 0. Displacement is also 0. But the distance, what distance did you jog? You jogged 2 miles. We might even note...
I have a question because I'm a little lost.
Yeah, go ahead.
I do not understand the basically what you're using like in short for things. So I know you said we went over some of that like no kind of like nomenclature or whatever above, but I don't know what the first one S and then is it S S S and then
S
SL.
subscript F is this first one.
Oh, it's
So,
an F. Oh.
so this is final position.
Oh, that means final.
Yeah, physicists love their subscripts like a lot. So in this problem, I use an F for final, and a 0 for initial. At various other times, you'll see me subscript with 1, 2, 3, or A, B, C to be specific about the situation at a given time or place. But yeah, lots of subscripts.
And then the last one is the actual displacement one.
So then this is displacement. And then this last one is distance.
Thank you.
Yeah, you're welcome. Thank you for asking the excellent question. Yeah, don't hesitate to interrupt me. I've been doing this for 15 years, so it sometimes can be not obvious where other people aren't quite haven't quite caught up to what I've said already. So feel free to interrupt and tell me I'm going too fast or I missed something. So, all right. So you jogged to Starbucks, you jogged home, got yourself a coffee. You jogged 2 whole miles, but your displacement was 0. You started on the couch, you ended on the couch. We might actually write your total displacement as a sum of the displacement to Starbucks. We'll call that delta S1. And your displacement from Starbucks back home. We'll call that delta S2. Displacement differs from distance because it takes position into account. Exactly. So our displacement from home to Starbucks, and we'll call going to Starbucks the positive direction. So we went 1 mile to Starbucks, still on the ground though. And then on the way back, we went a mile in the negative direction. And so total, the displacement is 0, even though we did definitely do some moving on the way. All right. Do you have any more questions on distance, displacement, position before I move on to velocity? All right.
So distance can't have a positive or a negative. Only displacement can, because displacement, you can go left or right.
That is exactly correct.
Okay.
So velocity is the amount of displacement divided by the amount of time it took. This is, maybe we would call this average velocity.
I'm sorry to interrupt, but on that last question, I thought distance was always positive.
Yes, I think that's what Logan was saying, right? That it doesn't make sense to talk about a negative distance because a negative sign implies the existence of a direction. And
Right.
yeah, and distance doesn't care about direction.
Okay, thank you.
Abigail, is that what you were asking? Okay. So if we were doing a calculus-based class, we'd be talking about derivatives right now. But we're not going to get into that. We're just going to talk about average amounts of velocity. So right, we'll write velocities as having an x and a y component, and there's some more subscripts again. But of course, we could also write that as the amount of displacement, or the distance, in the x direction divided by the time, right? And the amount of displacement in the y direction divided by the time. Similarly to displacement and distance, we will also talk about velocity and speed. Right, where speed will be the magnitude of the velocity. Right, and once again, to find the magnitude of a vector, we are going to use the Pythagorean theorem. Now I'm writing down a lot of math. You don't have to have all of this memorized. I'm writing it down in so many different ways because I hope that one of the ways will make sense to you. So once it clicks in some way, that's the way you should think of it. So these are all still in the realms of definitions, right? We haven't actually done any physics yet. For speed, is v still velocity or the vector? Yeah, so little v will be for velocity. V sub x and v sub y will be the parts of the velocity in the x and the y direction. And I'm already using s for position or displacement, so I'm not going to use s for speed. But sometimes I will just use little v with no fancy bits to mean speed.
Sorry, that confused me. So the v with the vector line above it, that's velocity, but a v that's just like naked is speed?
Is speed. Yep. I will try not to use this. I will try to always use this. But I am human, and sometimes I'll get a little notationally lazy. So sometimes you'll see the little v with no fancy bits. But I will try to always use the magnitude of the vector notation.
Sorry, this may be a silly question, but so that the first thing you wrote with the v and the two lines, that's the magnitude of a vector?
Yes. So
Okay.
I know it looks like absolute value signs, right?
Yeah.
But yeah, in vectors, though, we take that to mean the magnitude.
Oh, okay.
So we're repurposing a bit of notation, right? Because talking about the absolute value of a vector, in a sense, is the magnitude, right? Because if you take the absolute value of a number, what you're really asking is how far from zero is it? Whereas if we're talking about a vector, if you want to know how far from zero is the vector, the proper way to do that is to take the magnitude.
Thank you.
Yeah, you're welcome. Okay. So back to our Starbucks example. Let's say that it takes you 10 minutes to cover the 1 mile to Starbucks. And remember that it's 1 mile each way. Okay. What is your average velocity for the whole trip?
$10 a mile in whatever direction Starbucks is.
That's for the first leg, for sure. So maybe we draw a little diagram here. So here is, I need to use a different color. Here is home. And here is Starbucks.
Would it be 0? Because the displacement is 0.
You're right on track, Jillian. You've got it. So your total average velocity is going to be 0. Right? Because no matter how long the time is here, the numerator, the displacement, is nothing. So our average velocity will be nothing. But maybe we can do a little bit more in-depth analysis. Let's also say, for the sake of argument, that it takes you 15 minutes to drink your coffee at Starbucks. What is your average velocity on leg 1? And Kyle already answered this. Right? but your average velocity on leg 1 is going to be 0.10. So then what is going to be your average velocity on the way back? Yeah, on the way back, it's going to be minus 0.1. Now here's a bit of a difficult question. What is your average speed for the entire journey? Jolene is absolutely right. So the velocity is going to be the displacement over the time, but the speed is going to be the distance over the whole time. And in total, you jogged 2 miles, and it took you a total of 10 minutes on the way there, 10 minutes on the way back, 15 minutes at Starbucks. So in all, it took you 35 minutes. So whatever 2 over 35 is, that's your average speed. And Casey, yeah, I'm recording this not using the WebEx recorder, but using OBS. Yusuf, 35 minutes because it's 10 minutes on the way there, 10 minutes on the way back, 15 minutes at Starbucks. So that's 35 minutes altogether. Logan, I don't quite understand your last question.
Basically, I just don't know how we even got that 0.1. I can't really visualize it.
Oh, 1 mile in 10 minutes is 1/10 of a mile per minute. So
Okay.
0.1.
Distance over time. Distance over time for velocity
For speed,
or speed.
right?
So which one is this speed for whole journey? So the v with the vector over it. So we didn't find the velocity?
We did. The average velocity for your whole Starbucks journey is 0.
And math-wise, how did we come up to that? Like, what did we put over what?
Yeah, it's displacement over time.
Okay, thank you. Sorry, I just have to get used to all the symbols and stuff.
Totally. No worries. Nathaniel asks, why is V2 negative and V1 positive? Because they're in opposite directions, so one of them's got to be negative. And arbitrarily, we said that towards Starbucks is the positive x direction. Emily asks if there's a class standard for how many places to round. No, but like a reasonable amount. I know in chemistry there were sticklers for significant figures, and in your lab, they're going to be sticklers for significant figures. Here, I don't really care. Just make it readable. I like that you guys are helping each other out in the chat too. That's really nice to see. Okay. So we've defined displacement, which is a change in distance. We've defined velocity, which is displacement per time. We have one more quantity to define, which is acceleration. And we're just going to define that as the change in velocity per time. Right, we're going to write it as ax and ay. But that could very well be, right, change in x velocity, comma, change in y velocity. So we're not really going to talk about magnitude of acceleration too much, because in this class, our acceleration is always going to be a constant. It's not going to change. And almost always, the acceleration that we're dealing with, at least, and always for the first two chapters, it's just going to be gravity. So we're not going to deal with any situations in which we're not going to deal with any situations in which the magnitude of acceleration changes. There is also a technical term for the change in acceleration over time. Although, like I just said, for all the things that we're going to discuss here, there is no change in acceleration over time. But if there were, the term for this is called the jerk. I am not making that up. There is also a term for the change in jerk over time. If you were dealing with a problem where that was necessary, the change in jerk over time is called the snap. The change in snap over time is called the... Anyone want to guess what the change in snap over time is called? It's the crackle, that's right. And the change in crackle over time is the pop. Those are entirely real terms. Yep, this is still definitions. We are an hour into the class. We have not done any physics. All right. Does anyone have any questions on this page? They're all little v's on this page. I just have questionable handwriting. And little v here is always velocity. Later in the semester, if we have to talk about volume, I'll use big V. And because my handwriting is not amazing, I will probably put hats on big V if I have to write it. So that'll be my big V, and that'll be my little v. Okay.
We When you wrote the jerk, the very first formula for jerk, it was distance. Or, I mean, it was change in A. What's A?
Acceleration.
A. Oh, okay. Thank you.
All right. Let's talk physics. There are only 3 formulas from the first 2 chapters put together that you need to actually know. And I'm going to call them K1, K2, K3 for kinematics 1, 2, 3. So we defined acceleration as the change in velocity over time. So K1 should not surprise you. Our definition here is that our final velocity I'm going to call this velocity 1 instead. So our velocity at time 1 is going to be equal to our velocity at time 0 plus acceleration times time. Right, this one's not too bad. Since, this is if we solve for a here, we would have v1 minus v0 over t, and that's literally just our definition of acceleration from the last page. Yeah, K for kinematics, which is what the first 2 chapters are about. Kinematics is the study of movement. For K2, you are going to have to take my word for it, because to derive K2 actually requires a little bit of calculus. You have to integrate a couple of times. So for K2, our position at time 1. Oh, Emily says, is that acceleration multiplied by time? Yes, it is. For K2, it's going to be our position at time 1 will be equal to our position at time 0, that's where we started, plus our velocity at time 0 times time, plus 1/2 our acceleration times time squared. And on this one, you're going to have to take my word for it. There is a more lengthy justification in the book, but basically you have to use calculus to get here.
Sorry to interrupt. That first position 1, that's final position?
It might not be final because we might be daisy chaining a few of these together. We might have a time 1, a time 2, a time 3, right? But basically it's the next time. Does that make sense?
Yeah, I think so.
It'll make more sense once we do a few problems. I promise the back half of today's lecture is going to be all problems instead of me talking. Kinematics 3 doesn't require calculus. You just have to do some nice algebra. If you take K1, solve for time, plug it into K2, you get K3. Yeah, I'm just going to write this down. I want to make one note here. K1 and K2 are both 2D vector equations. K3 is a 1D scalar equation. So K3 can only be applied in one direction at a time. And you never have to use K3. You can always use K1 and K2. K3 is really just about convenience because it doesn't have any time in the equation. These are our tools to solve everything in the first 2 chapters of the textbook.
Sorry, can you repeat what it means to be a 2D vector and a 1D scalar?
Yeah, so in a 2D vector equation, you can consider the x and the y direction at the same time. For the third one, though, we can only consider x or y, but not both.
Thank you.
Okay. All right. Yep, these are our tools. This is what I call the beginning of our toolbox. What does change in x mean? Change in x means x1 minus x0.
So it's 2 times the acceleration times the change in whatever x is?
Mm-hmm.
Oh, okay.
Or equivalently, it could be y instead of x, but yeah, only it's one or the other. It's not both at once.
I just have another question. For K3, the A does not have like the little arrow over it, but for K2 it does. Does that have, or and K1 as well, does that have any significance?
Yes, that is on purpose. Because the K3 is not, they're not vectors. Right? All K3 is all just scalars and magnitudes.
Thank you.
Mm-hmm. There are other kinematic equations presented in your textbook, but they are all special cases of these 3. So your book might take one of these, solve for, say, velocity, and then present it as a new kinematic equation. It's not. It's just one of these 3 that's been rearranged. But all of you should be pretty decent in algebra by this point in your career. So I'd rather that you leverage the algebra skills you have and memorize less. I know, it's the first time in your whole pre-med careers that someone has told you to memorize less stuff. But here we are. All right. Are you going to have access to formulas, equations on the exams? You're going to have access to the entire internet on exams. Let's go back to our 2 friends playing catch. Now that we have some tools. I will say that this question that we started with is actually on the harder side of questions that I could ask you to consider from the first 2 chapters. But it also motivated us to talk about everything that we needed to talk about. So that's why I prefer starting with... and that's my general strategy. Start with something that you actually want to know about, and then build up the tools to be able to talk about it as you go along. So, what we... Megan, oh my gosh, that just means the problems are hard. maybe. But I mean, you all are going to use the internet anyway, so I shouldn't pretend that I can stop you from doing it. You guys are too much. So physics. A question that might be really natural to ask here is how, if person in red is going to throw the ball like they do, how far away should the blue-gray person stand in order to easily catch the ball? Right, so we're going to add one more vector that we're interested in here. We are interested in, right, the final position of the ball. The final position of the ball is going to be some distance in the x direction. It's still going to be 0 in the y direction, though, assuming that the fellow on the left is the same height as the red person. Jolyn says, do we need to consider mass? Not this chapter. That'll be next time. Depends on how well they catch. That is absolutely true. We're going to assume that these are two normally coordinated human beings and not, in fact, a couple of physicists. So the thing that we are interested in capturing from this problem is this x right here. What's the distance going to be? So let's use K1 to analyze this problem. And with that, we're done with step 4. Now we move on to the final step of our problem-solving process, and we just do the math. You are right. I did write that down as K2. Let's do a quick check for how many unknowns are involved here. We don't know the x, obviously, but we also don't know t. And so if we have two things that we don't know, it's a general rule that for two unknowns you need two equations, and then you can substitute and solve and find all your unknowns. Fortunately, our two-dimensional kinematic equations contain two equations inside of them. So if we consider just the x direction and just the y direction, that gives us two different relationships that we can leverage to do some solving and substituting. So in the x direction, let me make sure all the subscripts match up there. That's a 1. So in the x direction, our position at time 1 is going to be x. And that equals our initial x position, which is 0, plus our initial velocity, which I think someone helpfully calculated as 5.2. So 6 times cosine 30 is 5.2, I believe. And there it's a negative sign because it's going in the negative direction. So minus 5.2t plus 1/2 at squared, but acceleration in the x direction is 0. So we're done. That's what the movement in the x direction is going to look like. In the y direction, our y position at time 1 is going to be 0. Our y position at time 0 is also 0. Our initial velocity in the y direction is 6 sine 30, which is 3, because sine 30 is a half. And then we have plus 1/2 at squared. Acceleration in the y direction is just gravity. So g is about 10, and then we have the half out front. So that's going to be minus 5 t squared. Okay, so we've got equations written down in the x and the y direction. The x part has two unknowns. It's got both the x and the t in it. So if we can avoid that for the moment, we'd prefer it. So if we look at the y direction, though, we notice that the only unknown is time. The only thing we don't know on that equation is just how long the ball is going to be in the air. Jolene asks, how did we get the y? We just went and pulled the y component of everything that we had laid out in step 3. And yeah, we assumed the person was going to catch the ball at the same level it was thrown. It would be simple enough, well, because we assumed that, we were able to say that that y at time 1 was 0. That considerably simplifies the math here. If it was at some other height, then instead of having a 0 on the left-hand side here, we would have like maybe a half. In which case, now we would have to pull out the quadratic equation to solve for t. But if we assume that it's caught and thrown at the same height, we don't need to do that, and we can use we don't have to pull out the quadratic equation. Somebody just had a big ol' yawn with their mic hot. So the easiest way to solve this is probably going to be factoring. So if we factor out a t, we get t and 3 minus 5t, which tells us there's two solutions to this problem. There's t equals 0 is a solution, and also t equals 3/5 is also a solution. So the t equals 0 solution obviously corresponds to when the red person had just thrown it. So that's not the solution we're looking for. It's the other one, the 3/5. So it's going to take 3/5 of a second to get from our person in red to our person in blue. Ask, so before the plus in K2 is x and after is the equation for y. Sort of. I actually split it up into two halves. So the first half here, we took all of the x components, right? Because so the idea is that for a vector equation to be true, all of the x parts on one side have to equal all of the x parts on the other side, and all of the y parts on one side have to equal all of the y parts on the other side. So we split it apart into two separate equations, one with just the x parts and one with just the y parts. Emily asks, where did the minus 5t squared come from? The minus 5 is a combination of this half here and this minus g here, g being about 10. The 3 came from this 6 sine 30 over here. Let me write that a little neater, actually. Which we got from breaking up our initial velocity into x and y components. And the sine of 30 degrees is a half. So our initial velocity in the y direction is 3. All right, so very last step. So the position at which our friend in gray should stand is minus 5.2 times 3/5. I'm going to go ahead and round that 5.2 to 5. I know that's going to bother some people, but I don't want to pull out a calculator. So our final answer for the position of our friend in gray is about minus 3, the minus sign meaning that he should be to the left of our friend in red. Questions or comments?
You rounded 5.2 to 5. Are we allowed to do that on the exams?
As long as you note that you are rounding, that's fine.
Oh, okay. Thank you.
Yeah, I'm going to grade you on your ability to analyze a problem and apply physics, not on your ability to punch numbers into a calculator.
I know that we got t from y, but how would we calculate the y in that situation?
So the y we actually knew ahead of time, because we assumed that our two ball players were of equal heights. So our friend in gray was going to catch the ball at the same height that our friend in red threw the ball. And back in step 2 of this problem, we defined the height at which our friend in red threw the ball to be 0. So by definition, by conveniently choosing our coordinates, we were able to say that the ball started at 0 height and ended at 0 height.
So altogether, the coordinates would be negative 3, 0?
Yes.
Okay, thank you.
Sorry. So I know that like the negative cos, and then 30, that someone already calculated, but I don't know how to calculate this. Can anyone help me on this?
Yeah. There, two things I want to say there. If you've got a scientific calculator, you can get it from there. But also, there are some values of sine and cosine that we're just supposed to memorize, like we're supposed to have known after we took our trig class. So real quick, let me show you the table that I wrote on every calculus exam I ever took. Wow. There we go. So the important values The important angles that we're supposed to remember are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. The values of sine and cosine for these angles are all going to be divided by 2. And for those of you who have never seen the way I'm about to present it, you're going to wonder why your trig teacher never showed it to you this way. The values of sine for these angles are square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. For cosine, it just goes the opposite direction. Square root of 4, square root of 3, square root of 2, square root of 1, square root of 0. The sharp-eyed among you may realize that square root of 0 is 0, and that square root of 4 over 2 is 1, but I think that this is a much easier way of remembering it. Okay. If there are no more questions on this problem for now, I would like to take a short break. By my clock, it is 10:20, just turned. So let's take 10 and be back here at 10:30, and we will do 45 minutes of problems before we wrap up for the day. Yusuf, yeah, we're going to use radians later in the semester. All right, so I will see you all back here at 10:30. Welcome back, everyone. On our break, I had someone ask if I'm going to be available for one-on-one help. Yes, I do intend to have office hours. In fact, I intend to be in this meeting at 8 o'clock on Fridays, so there'll be 30 minutes for anyone who shows up early to ask questions, get help. And then I will also be holding some office hours during the week, as I don't know exactly when yet.
May I ask a question about this?
Of course.
So I know where we got the 5.2 from, which is just plugging in -6 cosine 30.